So we're dealing with section 4.3, which is about bases. Remember what a basis is. A basis is a set of vectors coming from a vector space that spans a subspace. It spans it, and it's linearly independent. So we've talked about a very famous subspace in the past called the column space, or the col of a matrix. And remember what the column space is. It's all the linear combinations of the columns. So it's the span of the columns of A. Span of A1 through A2 through AN, right? Now here's an important result. This will help us find a basis for the column space of A. It says, the pivot columns of a matrix A form a basis for the column space of A. So we're going to take the pivot columns of our original matrix, not of the row-reduced matrix, but the original matrix, to find basis for the column space of A. So let's actually prove. This one is provable. It's not that difficult to prove. We can actually prove this one. So let's say you have a matrix that's M by N. Let A1 have columns A1, A2 through AN. So it has N columns. Let this be an M by N matrix. So each of the columns is an Rm. And I'm going to call script B is a cursive B, consists of, I'm going to tell you what these guys are. These are columns that are going to be pivot columns. AK1, AK2, and so on, AKP. Well, I didn't write that correctly, AKP. Let these guys, the AKs, be all the pivot columns of A, be the pivot columns. So some of our columns, who knows, all of our columns A1 through AN could be pivot columns. But also some of them may not be pivot columns. It's possible some of them may not be. So, if you have any remaining columns, those will be the non-pivot columns, right? So, since the remaining non-pivot columns of A lack pivots, right? Then cutting grass. So I guess cutting grass is essential because everyone's supposed to stay home, right? Right. So since the remaining non-pivot columns of A lack pivots, then they can be written as a linear combination, It's a linear combination of the pivot columns. B, right, which consists of AK1, AK2, and so on, AKB. So, what we have A1 through AN, right? A1 through AN are a total set of vectors. There are a certain number of those vectors are going to have pivots. There's going to be a certain number that may not have pivots. The ones that don't have pivots can be written as linear combinations as the ones that do have pivots. So that means in total, all the vectors A1 through AN can be written as linear combinations, right, of the ones with pivots. So thus, the set of vectors A1, A2 through AN can be written as a linear combination of, come on, work, man, the ones with pivots. AK1, AK2, or AKP. So thus, it follows that B spans, right? B is that set of vectors with the pivots, right? This is B right here. So B spans the span of A1, A2 through AN. Now, what's another name for the span of A1, A2 through AN? Well, that's what? All the linear combinations of the columns of A. That's just the column space, right? The column space of A. So B, our set of pivot columns, right, spans the column space of A. Okay, so that's the first thing you have to show. When you're showing something as a basis, you have to show that your set of vectors spans your subspace. So we've shown that. We've shown that the set of vectors spans the column space of A. The second thing you need to show is that it's linearly independent. But we know that B is linearly independent, right? Because there's a pivot in every column. Yeah, so. Also, or I'll say moreover, B is linearly independent since the matrix that we create from the columns in B, since the matrix AK1 is your first column, AK2 your second column, AKP, that's your pth column. So, these are all pivot columns of the original matrix. So they all have pivots, since it has pivots in each column. So what do we have? We have that B spans a set of vectors, the set of pivot columns spans the column space, and it's linearly independent. So what can we conclude? Therefore, B is a basis for the column space of A. Okay, so there's a little proof if you want a proof. I don't think it's too useful though here. It doesn't really contribute a whole lot. So again, how do you find a basis for the column space of A? You just look at the pivot columns of the original matrix A. Look at the pivot columns of the original matrix A. Easy enough. We'll do an example of that soon. What about how to find the basis of the null space? Remember we also talked about the null space. The null space, it was a really big deal. Null space and column space were the two big subspaces we introduced. So remember what the null space is. We said the column space was what all the linear combinations of the columns of A. The null space consists of all the solutions to the homogeneous equation AX equals 0. So, theorem, not in red, it should be in black, is going to be about a basis for the null space of A. This one we're not going to prove. It's too complex to prove. The vectors from the parametric form of the general solution to the homogeneous equation AX equals 0. Form a basis for the null space of A. Now this one isn't hard to find a basis for either, the null space. So basically you're just going to solve the homogeneous equation like you've done in the past, AX equals 0. You're going to get a general solution. Oftentimes you're going to have some free variables, and then you just look at the parametric vector form of the general solution, and then just take out the key vectors that make up your parametric vector form. So I'm not going to prove that. It's too involved to prove that. But let's just do some examples. I mean, you want to be able to work example. That's what's important here. So let's do an exercise. Find a basis for the column space of A and the null space of A. All right, number 1. Here's my matrix A. Has columns 1, 2, -1, 3, 2, 4, -6, 5, 1, 2, 3, 1. Okay. So the first thing you always want to do when you're working such a problem to find the column space basis and the null space basis. It's going to be 2 problems basically. First, you want to row reduce your A. Row reduce it entirely. So here I go. I'm going to have what? 1, 0, 0, 0, 1, 0, 0, 0, 1, and I'm going to have 1/8, 23/24, and let's see, 1/6. So I did that in my calculator. Okay, so now we're going to work on the column space basis. So if you look at the row reduced form, this is what I'm going to call R right here. This is R. It has pivots in the first, second, and third columns. So that means when you're looking for a basis for the column space, you're going to take the first 3 columns of the original matrix. Now, a lot of students will take the first 3 columns of R. That is not correct. You're not going to take the first 3 columns of R. You're going to take the first 3 columns of A, the ones with pivots. So 1, 2, and 3 have pivots. So let's write B equals 1, 2, -1. It's your first vector, comma, your second vector. 3, 2, 4, comma, -6, 5, 1. That is a basis for the column space of A. That simple. Really simple to find a basis for the column space of A. Now I've already used the letter B, so I'm going to use a different letter for a basis for the null space. So for the null space, there's a little bit more work, right? You have to solve the homogeneous equation. So we solve AX equals 0, right? The homogeneous equation. So the homogeneous equation, you write it in an augmented form, right? A augmented with the 0 vector. It's the same thing as solving AX equals 0. That's going to row reduce to R augmented with 0, right? R, which R is the reduced row echelon form of A, right? So we row reduce A here, row reduces to R. And when you row reduce 0, it just stays the 0 vector. That's not going to change. All right, so what do we have? This is equal to now what? 1, 0, 0, 0, 1, 0, 0, 0, 1. And then on the right-hand side, we have what? 1/8, 23. No, I didn't write it correctly. Let me get rid of this. Here we go. Come on now. 1/8. 23 over 24. Right, this is still part of the row reduced form. 1/6. And now we augment it with the 0 vector here on the side. Okay, good. So now we have to solve this. So first of all, we're going to find what x1 is. All right, we have 4 variables, x1, x2, x3, and x4 for each column. So if we think about this row right here, that's going to be, so we know first of all that x4 is free. x4 is free because there's no pivot in the 4th column. That's key. So we're going to find x1, what am I saying x1 for? x3. Didn't go well, did it? So I get what, x3 plus 1 over 16 x4 equals 0. So that gives me x3 is minus 1 over 16 x4. Okay, now I'm going to find x2, right? I'm going to use this second row here. X2 plus 23 over 24. X4 equals 0. X2 is what? Minus 23 over 24 x4. Okay, let's find x1 now. Use that top row. x1 plus 1 over 8 x4. x4 is free equals 0. x1 equals negative 1/8 x4. So I'm going to focus on my general solution. So 1, x2, x3, and x4 is free. So x1 we got 1/8, x4. x2 we have what? Negative 23 over 24, x4. And x3 is negative 1/16. So we're now going to write the parametric vector form of the general solution. Okay, so here we're going to have a vector x. Right, it has 4 entries, x1, x2, x3, x4. The first entry is negative 1/8. x4, the second entry is negative 23 over 24. x4, next entry is minus 1/16. x4, and x4 is going to be itself, it's free. If you factor out the x4, you're going to be left with a single vector. Minus 1/8, so these are the coefficients, minus 23 over 24, minus 1/16, then a 1 here. So this single vector here, after the x4, that is going to be the basis of your null space. So I'm going to write here that, let's call it, this is a typical letter that's used, I've already used B, I've already used B for a basis, let's call this one E. So this single vector forms a basis, negative 1/8, negative 23 over 24, negative 1/16, 1. This single vector, the set containing the single vector, is a basis for the null space, is a basis for the null space of A. So what I'm basically saying is the null space of A, that's what all the solutions to the homogeneous equation, can be based on the single vector. And this single vector is linearly independent, right? Anytime you have a single vector, it's going to be linearly independent, unless you're talking about the 0 vector, which is linearly dependent. All right, so here it goes. Let's do a second problem where we do the column space and the null space, for example. So we have a matrix 1, 0, 3 in the first column, 0, 1, 2 in the second column, 2, 1, 8 in the third column. What else? 5, negative 2, what, 1 in the fourth column, and 6, negative 2, 4 in the fifth column. So the first thing we're going to do, we're going to RREF this dude. We're going to get 1, 0, 0. First column, second column is going to be 0, 1, 0. Third column is going to be 2, 1, 0. Fourth column is going to be what? 0, 0, 1. And what? 1, 0, 0 for the fifth column. So if you look at your pivots are columns 1, 2, and 4. Okay. When you're looking at the column space then, you're going to take columns 1, 2, and 4. And that's going to give you a basis. So B equals the set containing what? 1, 0, 3, 0, 1, 2, 5, negative 2, 1 is a basis for the column space. So please, whatever you do, do not take the 3 columns from the reduced form R. The reduced form, which I'm calling R, do not take the 3 columns from that. Take the 3 columns from the original matrix. Those are the pivot columns from A. You want to take the A pivot columns, not the R pivot columns. All right, so now we're working on the null space. So we're going to solve AX equals 0, the homogeneous matrix vector equation, also called the homogeneous system. Right, so you take A augmented with the 0 vector. That's how you solve it. It's going to be equivalent to R, right? A row reduces to R. I mean, you could do that the long way, but we already know, we've already done it. Above, we already row reduced. And this is going to be what? Bunch of zeros down the right side. Let's see, let's plug in 1, 0, 0, 0, 1, 0, 2, 1, 0, 0, 0, 1. All right, now we got to solve. I got everything. Oh, I missed a column. I got 1. I forgot a column. 1, 0, 1. Okay, so we said that 3 of our columns, 1, 2, and 4, are basic columns, basic variables. So x3 and x5 are free. x3 and x5 are free. Right, because these 2 columns don't have pivots right here. No pivots, right? Yep. Okay, so here we go. Scrolling, scrolling, scrolling. So we got to find x4. x5 is free, so next one to find is x4. Find x4. So using that last row, I'm going to have what? x4 plus x5 equals 0. x4 is negative x5. All right, let's find x. Don't need to find x3, it's free. x2. Use the next row for that. I'm going to have what? x2 plus x3 equals 0, so x2 is negative x3. All right, and then I got to find x1. Using the first row, I have what? x1 plus 2, x3 equals 0, so x1 is equal to negative 2x3. So now the general solution. This one's negative 2x3. x2 is negative x3. x3 stays as x3 because it's free. x4 is negative x5. And x5 is free. Okay, when I write down the parametric vector form now, of the general solution, That's going to be a vector x consisting of, let's see, 5 entries, right? Negative 2x3, negative x3, x3, negative x5. Dude is not writing like it's supposed to be. What else? x5. All right, you can factor out an x3 and you're left with negative 2, 0, 0, negative 1, 1. Those are the coefficients on the x3s. No, I missed some of them. I got screwed up. So it should have been negative 2, negative 1, 1, and then 2 zeros, right? Coefficients on the x3s and then the x5s. Squeeze these in. It's going to be what? 0, 0, 0, negative 1, 1. Yeah, so if you take these two vectors here, right, you're able to build everything from the null space out of those two vectors. So come on, scroll, thank you. So we're going to say E. We've already used up B, so I'm going to use E. That's the one that's used often. Consisting of these columns, negative 2, negative 1, 1, 0, 0, and 0, 0, 0, negative 1, 1 is a basis for the null space. Null space of A. Did I write that correctly? Let me just double check. Ooh. I missed something. Didn't I miss something? Totally missed something. So back here, I didn't see that 1. That 1 right there, that should have been like a 1x5, right? So I should have had an x5 in there. So when I would solve that, right, that x5, I would have minus x5. Yeah, so fixing this, there should have been a minus x5 here, which means there would have been a minus x5 here, which means there would have been a minus 1 right here, right? When we take the coefficient of that x5, it's a minus 1, which means this should be a minus 1. Okay, good, good, good. Well, that fixes it. Yeah, so be careful. Be careful. Not hard stuff, easy stuff. Yep, so that's how you find the basis of a null space and a column space.